Hello everyone. In this video, we will see some basic intensity transformation functions. As we all know that intensity transfer functions, these are among the simplest of all the image processing techniques. And in digital image processing, intensity transformation functions are the operations which are applied directly to the pixel values of an image, and their goal is to improve the appearance, then enhance contrast or highlight certain details. And these functions operate in the spatial domain, meaning they work on the image pixels directly. Okay, now suppose we have R, which is nothing but the values of pixels before processing, and S is the value of pixels after processing. So we are considering R and S as values of pixels before and after processing. And these values of R and S, these are related by the expression S is equal to capital T of R. This capital T, it is the transformation which will map a pixel value R into a pixel value S. Now here, as we are dealing with the digital quantities, so the transformation or the values of the transformation function, these are stored in one dimensional array, and mapping from R to S, it is implemented with the help of table lookups. So here for an 8-bit environment, a lookup table, it will have 256 entries. Okay, that is, if you have an 8-bit environment, a lookup table containing the values of capital T, it will have 256 entries. So now there are three basic types of intensity transformation function which is used for image enhancement. The first is the linear, under which you have negative and identity transformation. Second is logarithmic, where you have log and inverse log transformation. Third is the power law, where you have nth power and the nth root transformation. Okay, now one more is the piecewise linear transformation function, which we'll be dealing in the next video. This is the intensity figure for the intensity transformation function. Here we'll see what is the identity transformation, then negative transformation. This is for negative transformation. This is for identity transformation. Then this curve is for log. This is inverse log. You can see these both are opposite to each other. Now here even the identity is from this to this point, whereas the negative is opposite to that. Then you have nth power and nth root. Okay, so here this is the curve where you have it is like input intensity levels R versus the output intensity levels S. Now we will see the image transformation functions. The first one is the image negative, where it is also called as the inverse transform. So here the image negative of an image with the intensity levels in the range 0 to L minus 1. This is obtained by using the negative transformation, okay, which is given by the equation S is equal to L minus I minus small r, where R is the input pixel, S is the output pixel, and L, capital L, it is the total gray levels. So for a 8-bit image, you will be having L is equal to 256, that is total 256 gray levels. Now here, reversing the intensity levels of an image in this manner, okay, or it will produce the equivalent of a photographic negative. So here what we will do, you will reverse the intensity levels of an image, then you will get the photographic negative. Now this type of processing, it is used particularly for enhancing the white or gray details which are embedded in the dark regions of an image, especially when the black areas are dominant in size. Now here you can see this figure, where the first figure, it is the original image, okay, original image of a digital mammogram. It is a digital mammogram which is showing small legends here. Now here, even though the legends, these are visible, okay, that is, you have a visible content here in the, like, in both the images you can see the visible content, or it is visual, But some people, what they will do, they will find it easier to analyze the fine details of the breast tissue using the negatives. So what we have done here, you are taking a digital mammogram image, and this you are converting it to its negative, so that it becomes visually clearer. Okay. Now here, these image negatives, these are used in medical images, X-ray and CT scans, and also highlighting fine white details on the backgrounds. So image negatives, these are nothing but turning a photo into its exact opposite, where light becomes dark. Now next is the log transformation. So here the log transformation, these are generally obtained by using the formula S is equal to C log 1 plus R, where C is the constant and R, it is assumed that it is greater than or equal to 0. Okay. So here the shape of the log curve, it will show that this transformation, it will map a narrow range of low intensity values in the input to a wider range of output levels, and the opposite is true of higher values of input levels. So this type of transformation, it is used to expand the values of the dark pixel in an image, and it compresses the higher level values. So the opposite is true of the inverse log transformation. This is log transformation. Its inverse is inverse log transformation. And any curve which is having the general shape of the log transformation, which we have seen in the previous figure in the first slide, that would accomplish spreading or compressing of the intensity levels in an image. And here, this type of information, like whatever we do here, here it is not enough for the process where the power law transformation are much more versatile for such type of processes, which we'll see in the next slide. So here the important characteristic of the log transformation is that it will compress the dynamic range of the pixel values with large variations. Okay, and here you can see this is the figure where you have a Fourier transform, Fourier spectrum displayed in a grayscale image. Okay, and here what we are doing, we are finding the log transformation of this, result of applying the log transformation. You can see here you are getting bright colors. Wherever you are having dark one, these are replaced by the bright colors. So the log transformation, what it will do, it will brighten the dark areas while preventing the bright areas from exploding in intensity. Okay, so what we'll do basically here, we'll brighten all the dark areas and will prevent the bright areas from exploding in intensity. So here this log transformation, these are useful for expanding dark pixel values and they become more visible, and it also compresses the bright pixel values so that details in very bright regions do not get washed out. And the applications for log transformation are here it is used in like images with a very high dynamic range, then Fourier spectrum visualization, and improving the visibility in the dark spots. Next, coming to the power law or gamma transformation. Power law transformation, it is having the basic form as S is equal to C R raised to gamma, where C and gamma are the positive constants. Now here sometimes this equation can also be written as S is equal to C into R plus epsilon raised to gamma. So here it will add a small offset which is the measurable output when the input is 0. Now this figure shows the plots of gamma for different values of gamma here. Okay, and here the power law curves with fractional values of gamma, it will map a narrow range of dark input values into a wider range of output values, with opposite being true for the higher values of the input levels. And when the curves which are generated with gamma greater than 1, these will be having opposite effect as those which are generated with the values of gamma less than 1. So here you can see this line is for gamma is equal to 1 and these are for gamma less than 1, and this side it is gamma greater than 1, and both are opposite to each other. So these will have opposite effect. Okay, whenever you have gamma greater than 1, gamma less than 1, both will be having the opposite effect. Now the brightness or the overall brightness, it is controlled using the gamma. That is, if gamma is less than 1, then the image becomes brighter, and if gamma is greater than 1, the image becomes darker. And the exponent in the power law equation, that is referred to as gamma, and the process which is used to correct these power law response phenomenon, it is called as gamma creation. So here this uh, power law, it is used in uh, displaying devices like CRT, LCD, or which perform the gamma correction. So here the cathode ray tube, that is the CRT tube, it has an intensity to voltage response, that is a power function with exponents varying from approximately 1.8 to 2.5. And here the gamma correction, it is important if displaying an image accurately on the compact screen is of concern, and the images which are not corrected properly, these can look either bleached out or these will appear like too dark. So here whenever we are trying to reproduce the colors accurately, then it requires some knowledge of the gamma correction, because varying the value of gamma changes not only the intensity but also the ratios of the red to green to blue in a color image. Okay, so gamma correction, it has become increasingly important in the past few years as the use of the digital images for commercial purpose over the internet was increased. So you can see this figure here. This is the general purpose contrast manipulation. That is this gamma correction. It can be useful for the general purpose contrast manipulation. This is the original image. Okay, and this is the gamma corrected image, and this is the original image viewed on a monitor with gamma of 2.5. Okay, so this is the gamma corrected image. So this was about the basic intensity transformation functions. Hope you have enjoyed the video. Thank you.